Well, very good day to all of you, and here we are continuing with the virtual classes of science. We are in the discussion of rotational dynamics. Like in the last sessions, we have already studied a few concepts like torque, and we have introduced ourselves into the angular momentum, and we have seen how to get the moment of inertia of different system of particles. And this is our time to learn the moment of inertia and angular momentum relationship, or we are going to define angular momentum in detail. That is the aim of this session. I am Shabu Subramanian, inviting all of you to the session of angular momentum and moment of inertia. So we have already seen these relationships, how the torque is defined as R cross F, and this is equal to I into alpha. It is very similar to mass into acceleration in the linear or translational mechanics. And the moment of inertia of a system of particles is given by sigma I is equal to 1 to n mi ri square, where mi are individual particles' masses and ri are their corresponding distances from the axis of rotation. And also we have seen the second law of motion in rotation, which is tau is equal to dl divided by dt, similar to F is equal to dp divided by dt. Force defined as the rate of change of momentum. Similar to that, torque is defined as the rate of change of angular momentum. And also we have seen angular momentum can be expressed as cross product of R and P. So let us see what is angular momentum of a particle and how does it refers or how does it relate to the moment of inertia of a particle or a system. So suppose we have a particle situated at this point with mass m with a position coordinate r with respect to an origin O, or we may say an axis passing through this one with respect to an axis passing through the origin. And if the particle has got a velocity, or if this has got a velocity like this, we can say that R and B are making an angle theta. R and B are making an angle theta. So from that you can see the angular momentum can be defined as the cross product of R and B, or RP sine theta, and the linear momentum of the particle. Since m is the mass and v is the velocity, linear momentum can be expressed as m into v, or this can also be written as mvr sine theta, the most general expression. So I can say L is a cross product of R and P, and this gives the magnitude of angular momentum. And what about the direction? The direction of angular momentum will be R to B. So look at that, it's a rotation anti-clockwise. So the direction will be out of the plane of the paper, or that is perpendicular to R and B with the property of the cross product. So we can say direction of L will be perpendicular to R vector and B vector, or we can say L, E, L, R, V, all of them are mutually perpendicular to each other. So we got the magnitude, we got the direction. So what is angular momentum? Mathematically we have defined it as the cross product of position vector or position vector with the linear momentum of the particle. We can say the SI unit of this one will be, momentum has got kilogram meter per second, and another R is added, so kilogram meter square per second will be the unit, because kilogram meter per second is already there with this, and another R is introduced, so kilogram meter square per second, and the dimensional formula will be ml square t raised to minus 1. This is the simplest definition we can obtain for angular momentum in terms of R and P. Now we are going to extend this one into the case of single particle, system of particles, and we will see how that can be defined in the terms of moment of inertia. So let us take the case of a single particle which is rotating about an axis, just like we have considered in the case of moment of inertia of a single particle. If this is rotating about an axis with an angular velocity of omega, suppose the particle has got a mass m. From the axis it is at a distance of r vector's direction, this is r, and it has got a tangential velocity, so vt. We can say that vt and this is making 90 degree, as well this also making 90 degree. So we are going to write the expression for angular momentum for a single particle revolving about an axis. Angular momentum for a single particle. Why I am doing like this is, if you study for a single particle, it is very easy for you to understand the concept, and you can simply extend that one into the case of many particle system. And for a single particle, we have got the expression for L as R cross P, or I will write it as R cross MV. From this you can see R and V makes 90 degree with each other. So R cross V will give you maximum value, which is RV sin theta. Sin theta is 1, this becomes RV. I can write this expression simply as RMV. And when we were discussing circular motion of particles, we have seen that this velocity tangential is related to the angular velocity as omega cross r. This is the relationship between linear velocity and angular velocity. Linear velocity and angular velocity. And from here you can see omega is perpendicular to the plane and r is radial, so this is also equal to 90 degree. I can simply put it as omega r. So this v can be replaced by omega into r, just like we are replacing linear terms with angular terms. This will be r m omega r, or r into r is r square. I can write it as m r square into omega. So the angular momentum magnitude is given as m r square omega, and the direction of angular momentum, as I said, will be in which direction? That will be purple, r cross p. It's an anti-clockwise rotation again, so angular momentum will be in the direction which is along the axis of rotation, or that will be along the direction of omega itself. So you can see L is equal to mr square omega gives the expression for angular momentum, and this is very similar to a linear momentum equation. P is equal to mv, omega in place of v, so we can say m is replaced by mr square. That is nothing but that is the moment of inertia of a single particle. So since I is equal to mr square, so what we have obtained is we can express the angular momentum of a particle as angular inertia or rotational inertia or moment of inertia multiplied with angular velocity. So this indicates what? The amount of rotational motion or amount of rotational motion content of the particle. So we got the relationship between L and I, and that is through omega for a single particle. This is very simple to understand if you have got the concepts of cross product and to represent the rotation of a single particle. Now, like we have done for many particle system, I hope all of you have got this idea. I am extending this one into the case of many particle system. What we can do is, I am just replacing this one as from single to many particle system or a system of particles. system of particles. That means instead of one particle m1, this is r1, I have got m2 at r2, m3 at r3. Similarly, if there will be n number of particles, like this is the axis, this can be mn at a distance of rn. Extend the concept. This is for, I am taking this one for an ith particle, ri cross pi, ri cross mi vi, all for the first particle or ith particle, ri mi vi for that single particle or ith particle, ri mi omega I ri, mi ri square, omega I. If it is a rigid body, we can say omega 1 should be equal to, omega 2 should be equal to, omega 3 equal to omega I should be equal to a constant value. So I can replace omega I with omega. This is the expression for single particle's angular momentum. So to find the total angular momentum, I can take L is equal to sigma I is equal to 1 to n Li summation over all particles. I is equal to 1 to m mi ri square times omega. What's the quantity within the bracket? That is nothing but that is the moment of inertia of the system of particles. So we have expressed the angular momentum in terms of the moment of inertia, and this is very similar to which one? P is equal to mv. So this is another way to derive the expression for the moment of inertia. If the question is given like derive moment of inertia starting from angular momentum, you can follow this procedure. If the moment of inertia have to be derived from the torque, you can use the procedure that we have done in the earlier session. So this is the way to analyze moment of inertia of a system of particles, single particle, and understanding of moment of inertia, angular momentum in terms of moment of inertia. So to conclude with, what we have done now is the angular momentum of rotation of a system of particles is L is equal to R cross P, or this can also be written as I into omega, which makes our second law very much sensible right now, because L is equal to I omega is similar to P is equal to mv, and dou is equal to dl by dt is similar to F is equal to dp divided by dt. So you can see what I told in the formation of the flow chart of the rotational dynamics. All the equations are repeating, or that is getting duplicated when you are coming into the rotational dynamics. So there is nothing new, only a few concepts, mathematical concept, I will say. Rotation, moment of quantities will give you the analogous quantities of rotational dynamics. So like you have learned what is the torque in terms of cross product F, and how the torque can be defined by using the second law, how the angular momentum arises, and how the angular momentum is related to moment of inertia, and what is the expression for moment of inertia of a system of particles and single particle. So all this will be useful for you while you are doing the problems related to the rotational dynamics. So this makes a very simple approach to the derivation of moment of inertia and angular momentum of system of particles. Thank you all, and I hope all of you have enjoyed the session.